previous problems or anything I want to talk about? Or maybe you're like, wait, we have homework due? What is due today? Oh, a bunch of stuff. 11.4, 11.5. Again, try and get stuff in on time. If you're running into issues for various reasons, just make sure you get them in for sure. I will try and do my best to grade everything. But yeah, 11.4 and 11.5 are technically due today. So, questions about either of those? Let's see, what were those again? 11.4 is on the unit tangent and normal, and unit 5 is on the arc length and the curvature calculation. They're pretty straightforward, formulaic, but the algebra in there can get kind of messy. Well, we may have time at the end if that sparks your brain to go, oh, I probably should look at that. So yeah, so limits. I mean, we have functions of multiple variables. We start talking about limits, and this leads naturally into the next thing, which is derivatives. You know, what do derivatives of these things look like? Now that we have limits, go back and go, okay, limits and derivatives. I'll remind you of that in a second. How does that actually tie into things? And so this is, I'm going to leave a little word here for a second. I think I might have already said it, but I don't remember. So these are not only derivative, but the derivative, but derivatives. You're like, ah, here we go. And I'll fill in this word in a second. Good. Sure. So the old approach here, if you remember, was we have a function f of x, and we go in and we pick a particular point, and sometimes we put in like a, or yeah, I guess we do that. But I'm just going to use everything as x, so if it's not too confusing. So we come along and we want to figure out what the slope is at that point. So this is like x. Let me get rid of this other one so it's not too many x's flying around. And we're like, okay, so how do you do this? How do you do the slope at a point? Well, you can't. You need 2 points in order to do a line. So we're like, all right, but I want to know what the slope is there. So I pick a point that's really close. And by doing that, but one way to do that is just to add a little bit onto what you have. So this h, for some reason, got in there. So you go x is a point. X plus h would be another point. And you can draw that. So both of those things I can plug into my function. So I get f of x in the first case. And if I plug the second one in, I get f of x plus h. And it's inside the parentheses. So the x plus h occurs first, then it goes in the function. And so I'll have a little distance there, and I'll have a little distance there. And if I move this one over here, I get a nice rise over run. Here, so there's the rise, and there's the run. So the slope of that line is equal to change in y over change in x, or the rise over the run, or let's see, the run will be the difference between these x values, which is from x to x plus h, that's h. The rise will be the final value, f of x plus h, minus the initial value, f of x. So it's just the change in y over the change in x is the slope. And that's called the slope of what's called the secant line. It's not quite the tangent yet. So it's just 2 points from the function here, and so we get, the function will pass through those 2 points, but I really want to know what the slope is only at this one point. Like, what is the slope of the graph? Is it going up, down? How steep is it? Only at that one point. So this is where we impose a limit, where we let this h shrink down closer and closer and closer and closer to x, and the secant lines will sort of sweep in to get closer and closer and closer to what we think should be a good approximating line called the tangent line. And so we just take the limit of this fraction and we give this a name. So this is going to be equal to the slope of the tangent line. been doing over and over and over, but it really does come from this property here, that everything does come from a limit. We do a bunch of these initially, and then we're like, man, that's way too hard. Let's figure out some shortcuts on it. And so we do. But we also give this some notation, and this is what we're going to alter today. So we're still in the old case here. The notation for this limit h goes to 0, x plus h minus fx over h, which has its own algebraic challenges sometimes. We'll write this, sometimes we'll write it as f with a prime on it, and sometimes we're going to write it as this symbol here, where it looks like a fraction. We can treat it as a fraction, and so df dx, or yeah, df dx is the way we read it. And in both of those cases, this is called the derivative. It represents a rate of change. So for every unit you go along x, how much does your function change approximately? It represents the slope. You know, is it going up or is it going down? So all of those things held, but it didn't rely on the fact that this limit has to exist. And sometimes it doesn't. If you hit a corner in your graph, this limit will not work. So the graph has to be at least kind of nice and flowing, what we call smooth, in order for all these things to work. If you have breaks or hard corners, or called cusps, this thing won't work. So there's that. Now, this one, this notation, we're going to abandon because it's not going to work anymore. We can't just talk about the derivative or the prime, because not only do we have an x, you know, we're going to now have a y. So we're going to have different ways that these limits can occur. And instead of doing derivatives before I go on to the next one, these are going to be called partial derivatives, where we won't get the whole derivative, we'll just get a part of it. That's why it's called partial derivative. So all that stuff we're going to try and reproduce, except now we've got a z equals f of xy. So we've got two independent variables, x and y, and both change. So what do you even mean by slope or rate of change if you have like multiple directions of possible change? So we have to figure out how to deal with that. So we start off by just saying, well, let's try the slope in the x direction. So what that means, we're going to think, is that y is not changing. So y will be a fixed value. And we leave y fixed, and let's only change x and see what happens if we do that. This will be like, we're looking east and west on a map. How much does the graph go up and down if we're looking east and west? We could be looking straight down the mountain, or we could be looking along a path along the side of the mountain. So we could have a very flat slope one direction, but you turn and now all of a sudden, boom, you're going straight downhill. So you'll have directional slopes in this one as we go. And this is where pictures will be nice. I'll try and sketch as many as I can, but they're also good pictures in both. Okay, let's do this. So the slope in the x direction, that means I want to do something like this. It's the same thing, the rise over the run, except only x will get an h on it. Y is fixed. So it'll be f of x plus h and y minus f of x, y. So it'll be like the rise. And the run is still going to be h. And I take the limit of that guy as h goes to 0. So it looks very close to what we had on the previous one. Now we just have this extra y sitting there. And if this works, if this works out, this will be called the slope in the x direction, the rate of change in the x direction, or you can talk about the derivative in the x direction. So derivative in the x direction. And there will be multiple notations for this. First one will be, we can't use prime anymore, and so we want to go back and try and use df dx. But I can't write this because that's really particular to just one variable case. So this is where we introduce this new notation. We still want to write something that looks like a fraction with f and x. We still want to write a d, but I don't want to use the regular d. So we put in a different d. And this is, I don't know where exactly this came from, but it looks like a curly d. And it's still read df dx. df dx. Maybe just phonetically here. I still read it as df dx in words. It's just called the partial derivative. The derivative in the x direction will be partial derivative in the x direction. And so that's going to be one way to write it. Sometimes we're going to write it like this, where we write f with a little subscript. So that'll be nice for shorthand, is where we may write it like that. And it just means the exact same thing. Or we might write it as this curly d, z, dx. So instead of using f, we can use z. Just like in the previous slide, I didn't write it in, but you could have written that, just for completion in the notes, you could have written this as y prime or dy dx. I guess technically we could have written that in the previous slide. And now I'm going to do either df dx with the curly one, this is actually called del, the del symbol, or fx, or dz dx, or we can write this as z sub x. That might be another way we write it. Or, and this may come later, and you definitely will see this in differential equations, is they'll write it as a capital D sub x of your function. So that's another way they might write it. This is like the derivative process for x applied to x. It's like sort of another function applied to your function. Or it's a process applied to. Well, all those things are possible as being the derivative of the slope in the x direction. Similarly, you can talk about the slope. I'm not going to write all those things out. But the slope in the y direction. You just do the exact same thing. Where x is fixed, and you do the limit as h goes to 0, but now you don't change x. So instead of the h going on the x, it goes on the y. So it's f of x comma y plus h minus f of x y all over h. And if this works, it'll be the derivative in the y direction. We can write this as the f dy, or we can write it as f sub y, or we can write it as dz dy, we can write it as z sub y, we can write it as d sub y. I guess technically d sub y z can go in there as well. So great, now we have a lot more to deal with here. Don't worry, we're going to do plenty of examples of how this kind of thing works. But that's notation. And by the way, that's the first partial derivative. So we have the first derivative on the last slide. Now we have two first partial derivatives. So if you're getting worried, you should. Because now we can do a second derivative. And how does that come into play? So if we tried to do, in the old case, the second derivative, then let's see. We had our function y equals f of x, and we took one derivative. We could do f prime, which we call dy dx. Oh, sorry, y prime equals y prime, f prime, dy dx, df dx, all of that stuff. If you did it again, you would write it as y double prime, so 2 primes. You could write it as f double prime. And now this other part here, if we unravel exactly what's going on, technically it's like this. It's the derivative of the first derivative. So if we write it as the fractional, if you're ever wondering why the 2 is where it is in this thing, why isn't it like d2, d2? Then that's the droid that didn't make it in the Star Wars. Then this is the operation, which means take the derivative. This is the first derivative. So you get 2 d's, and so that's why they write it as d2 y. On the bottom, you don't really just get two d's, you get two dx's. So it looks like that. So it's two d's and two dx's. So you could write it like that. Now, after a while, like everything, you just like drop the parentheses, and this turns out to be d2y dx2. Although really that 2 is not on the x, it's on the dx. And we got sloppy and lazy. Anyway, if you're ever wondering where that came from, that's exactly the application of it. Now, the new one is, I'm going to draw it from the top as kind of a tree here. We've got f of xy. I'll drop the xy here in a second. And we could use z all the way through if we wanted to, but let's see. So if I took a derivative in x partial derivative, then the first derivative would either be written as f sub x, or I could write it as df dx. So either one of those two notation works if I do an x derivative. If I do a y derivative, then I would write it as fy, or I could write it as df dy. So those are the first partials, the first partial derivatives. But now, what happens if I take a second derivative? Well, which one do I do? Do I do the left or do I do the right? And the answer is yes, you do them all. So not only do, in the first case, do I have one derivative and I got one second derivative, now I've got two first derivatives, and I'm going to have four second derivatives. Because on each of those, I could either do x or I could do y. And on the y, I could also do either x or I could do y. And so I'm going to have four what are called second partials. And it does keep going on. If you ever did a third derivative, you'd have 8 of them, 8 different ones. So notationally, what does this look like? We'll do notation and then we'll talk about how do you actually compute it. I don't want to do the limits because it gets hard. So I'm not going to do that. So let's see. So if I took my first derivative and I wanted to do the derivative again, then the answer is I would write it as fx, and then I would take an x derivative, and you could write it like that. And that's nice because I put a subscript whenever I want to do a derivative. But I'm starting not from f, I'm now starting from the first partial. So I could write it as f sub x, sub x. And again, as normal, we're like, too many parentheses, let's just screw it and just write f sub xx. And that's what we write. The problem is you have to interpret what that means. It means do an x derivative, then do another x derivative on top of it. How about this other notation? Well, technically, it's like I want to do a partial derivative of the partial derivative. So it looks very similar to the one that I had, and I do write it like that. It's d2f over dx2. And yeah, technically I need parentheses on the bottom, but throw them out. So that kind of hopefully looks very similar. It's xx, it's got the 2, it's got an x, the d's are weird, but whatever. We get that. On the far side, and I'll fill in the middle, it looks very similar. We could either write it as fyy, because it's y and then y again, or it's y and y again with the partial derivative. So d2f over d2y. So we can do that. Now it gets a little tricky here in the middle that I want to do a derivative with respect to x, but then on that do a derivative with respect to y on that answer. So let's try and be a little careful on this one here. So that means I take my f sub x and do a derivative sub y. So any subscript means do the derivative. So I can write this, hopefully not too surprising, as fxy. All right, that looks good. How about this one? Hey, we're on a roll here. So we do y and then x, and that means I do f sub y, and then I do a subscript on that, sub x, so that'll be fy and x. Okay, that seems to make sense. Here's one that, like, when you first see it, you're like, what? What's going on? But if you write it carefully, saying if I do a y derivative, that means to put the operation of take a derivative in front of what you're taking the derivative of. So in this case, it's now using the d's. I get the derivative d dy of df dx. And keeping the order in the order that it is, the d's will hit and get d squared. So what's going to be on the bottom? It will be dy and then dx. So just writing it in the order that it appears. Now this is where it looks a little confusing, because if I use the subscript, the cat is walking on my piano. If I use the subscript format, the x goes first, then the y. If I use the fractional formation here, derivative, it looks like the reverse. And this is one thing just to be real careful of. The subscript is nice because whatever is closest to the f happens first, and then after that, that derivative happens. And if you have another one, that derivative happens. Whereas this one, you have to really interpret it to go, what does that mean? It means, it does mean to do the x derivative first, then the y derivative. So you have to read either left to right or right to left, depending on which one you're doing. So if you followed all of that, then this one here means take fy, df dy, do the x derivative to it. So that means that the d over dx goes in front, and therefore we get d2f over dx dy. And it's the reverse. It's again the reverse notation. And that's unfortunate, but it's one thing that you've got to be careful of when you do it. So, examples. That's too much theory. Do some examples. So, here is one. Let's do z equals x squared y plus 3x squared plus 4y minus 5. Find all these partial derivatives. We'll see how far we can go with it. Okay, so first partial derivatives. Z sub x. Remember, this is the key, is that if you're doing an x derivative, that means you're doing the slope in the x direction. So y is fixed. That means that you can treat y as a constant. When you're doing, when you're doing an x derivative, y is not changing. So really you should just say, okay, I'm going to think of y as a constant when I'm doing my derivatives. So in this case, the y that's on the x squared is like a constant multiple. The y over here, this 4y, is constant. It's not changing. So when I do the derivative on this, I can use the constant multiple rule. We're thinking of y as the constant. So how do you do a constant multiple rule? You take the derivative of your function, 2x, and then you just multiply on by that constant multiple. So that first part would be 2xy. The next one is a regular one. It's an x derivative, so that one is just straight up 6x. It's a constant multiple 3, but then times 2x, so we get 6x. The 4y, because, again, just repeating, I'm thinking of x as constant because I only want to let x change. That derivative is 0. And this last one is a constant, so that derivative is 0 as well. So that means that my z sub x is just 2xy plus 6x. So there's one of the first partial derivatives. If I repeat this process for y, so if I wanted to do z sub y, then in this case, x is fixed. Or you can think of it as x is a constant. We're only looking like north-south on the map. The x is not changing. And so in this case, x squared is a constant. This 3x squared is a constant. So if I took the derivative of the first one, the x squared would be my constant, and I take the derivative of the y. Now, I'm doing y derivatives, and that would be The next one, the 3x squared, x is constant, so that's like a constant, the derivative is 0. For y, that's just a regular derivative, so that derivative is 4. And then the 5 is also constant, so that derivative is 0. So in this case, I would get that z sub y is x squared plus 4. So those are my first partials in here. And you can see they're different. I mean, they're typically going to be radically different from each other. So I'm not going to put this all in that. If I wanted to do zx and then x again, if I wanted to take the second partial, zx, and what that means is it means to look at z sub x and do the derivative of that one now with respect to x. I want to do the derivative of this with respect to x. So 2 is constant, and now I'm doing another x derivative, so I want to think of this y as constant. So if I take the derivative of 2xy, then I just get 2y, technically times 1, because I take the derivative of 1, but the rest is a constant. The 6x is just the same, so I get 6, so that's 2y plus 6. Will be that second partial derivative. Zyy, so we look at the y derivative, and then we do another y derivative of that. So we look at this. It's a y derivative, x is constant. If this x is constant, this 4 is constant, everything is constant, and so the y derivative is just straight up 0. We will be relating to this thing to like concavity and stuff later, but it's going to be tricky because there's like a mixed, one direction might look like one kind of concavity and the other might look like another. So we'll have to figure out how best to do that. So those are the straight up just x, x, and y. What about the mixed ones? So the mixed partials meaning x, y, and yx. So this means I do x first, and then y is second. So I've done x first, and I get to this one. Now I want to do the y derivative of my x first derivative. So x is considered to be constant in this case, so we have a constant multiple to x. And then 6x is constant, so that part is going to be 0. So I just get 2x for that derivative thing. What about, to complete it, I'm going to do plenty of examples here, zyx. So that means you do y is first, and then you do x second. So we want to look at the y one first, and now do x, derivative of that. And that's pretty nice, because it's all x's and constant. So I take the derivative of x squared, I get 2x, and I take the derivative of 4, and I get 0. So I also get 2x. Okay, so my derivatives are the 2 first partials and the 4 second partials down here below. So we got that. So let's just try more of those. Z equals the sine, sine of 5x squared plus 2y cubed. Find all the partial derivatives. Maybe I can make my tree here. Let's try. If I do my x derivative on one side and I do my y derivative on the other side, I'll get z sub x and I'll get z sub y. So let's do the x derivative. Okay, so x derivative, x is inside of a sine, so that means I'm going to have to do a chain rule here. Chain rule. And I'll take the derivative of sine, which is cosine, 5x squared plus 2y cubed. And then I got to multiply by the derivative on the inside. So the derivative of the inside, this one's easy, that's 10x. And now, again, I'll keep repeating it until you're sick of hearing it. anything that's in terms of y when you're doing an x derivative is a constant. So the second part is 0. That 2y cubed becomes 0. On the other hand, if I do a y derivative, well, it's still a chain rule here. Sorry. Should just write CR. So the derivative of that one is cosine of 5x squared plus 2y cubed. That's the same thing. But now it changes when I do the derivative of the side. X is now considered to be constant, so that 5x squared term disappears. And then I do a regular derivative of y, which is 6y squared. So here's my two first partial derivatives. X, it's very similar. I get a 10x, the other one gets a 6y squared. So now if I try and do this, where I take this, and now I'm at zxx and zxy. If I chain off of that one, if I chain off of this one, it would be zy and then x versus zy and then y. Okay, so now I got to take the derivative of this with respect to x. Problem is I have a product. Great. So I have to use a product rule here. And here we go. So it's the first, so that's cosine 5x squared plus 2y cubed times the derivative of the second. So the second is 10x, so the derivative of that is 10. Plus the second, so that's 10x, times the derivative of the first. And it's the x derivative again. So anything that's y is going to disappear. So I take the derivative of this cosine, and now this one is going to be a chain. So negative sine 5x squared plus 2y cubed. Then I multiply by the derivative of the inside, chain it, and that's going to be 10x. Just like we had on the first part. So that's the zxx using the product. You could clean it up, but I'm not going to worry about that right now. This one, you could do zxy, so that means x, and now we do the derivative with respect to y. Now it looks like it might be a product rule, but again, the 10x is a constant multiple. So I just have to worry about constant multiple. I'm still going to have to worry about chain rule, because I have the y squared inside of the cosine. But if I did this, I will get 10x as my constant multiple. Take the derivative of the cosine, which would be minus sine 5x squared plus 2y cubed. And then I multiply by the derivative on the inside, which is going to be 6y squared. So yeah, that constant multiple is out front. I just got a regular cosine derivative with the chain rule derivative on the inside because it's y. Zyx, take the derivative of this thing here now with respect to x. It looks like a product, but it's not because the 6y is a constant. So a constant multiple along with chain. So I take the derivative of this thing. I will have the constant multiple 6y squared times the derivative of the cosine. So minus sine 5x squared plus 2y cubed times derivative of the inside, the chain part, and that's going to be 10x. And then just to complete it off, we do y. We got to do y, and then we do y again. And now I do have a product of two things that have y's in it. So it's going to be product rule again. And of course, the chain rule when I do the interior. So the product rule, let's see, first, cosine 5x squared plus 2y cubed times the derivative of the second. The derivative of 6y squared will be 12y. Plus, I'm running out of room, but I think I can squeeze it in, plus the second, 6y squared, times the derivative of the first. So it'll be minus sine 5x squared plus 2y cubed times, there's managed to squeeze it in. You can read that small, okay? Times 6y y squared. So that's changing. I kind of hope I don't have to do like a third derivative in here because I'm going to have a bunch of product rules flying around. One thing to notice, and maybe you already did notice, is in the middle, look at that, zxy is equal to zys in this case. Because they both have 10x, they both have 6y squared, and they both have the same sign, and they're both negative. So in this case, they are the same in this case. And in the last problem, they were the same. So the actual question, of course, is, are they always the same? Well, we checked it for two cases. That's probably not enough. We might have just lucked out. So we can try some more, and then maybe next time we can talk a little bit more about that. This is now a good practice on revising your derivative skills. I'm just going to do one more example, and then I can see if you have homework questions and then touch loose. This is now before you might have said, all right, here's the function, find the derivative. That's all well and good. But how about the reverse? If I give you the derivative, can you find the original function? Can you start getting into integration or maybe guesses and checking? Now it's a little bit harder because, and this is example 27 in 12.3, is it says, I can't just give you the derivative and tell you what, try to figure out what the original function is. I have to give you both of the first partial derivatives and see if you can recreate the function off of that. So if I'm telling you the answer for the derivatives, can you give me the function back? And this is where it starts to get a little bit harder. You do this in DiffyQ, so if you take in differential equations, this is related to things like called exact equations. Bringing back bad memories here, maybe. So the first partial derivative for x is sine y plus 1. The first partial derivative for y is x cosine y. And the question is, can you recreate the original function from that so that if you then went back into the partial derivative, you get this? So, okay. How would you do that? Well, you can kind of try and start on one of them and kind of then try and start on the other one and then see if you can merge the two things together. Maybe. Or maybe you can just guess. You're like, let's see, okay, if I took a y derivative and I got cosine, that must have meant I started with a sine. But over here, if I took an x derivative and I had 1, that probably meant that I had an x. And I had sine, but this is now constant, so how do I deal with that? So this is the first try on this, just using the first one. I would guess that, well, how do I get sine y if that's a constant? That had to have been a constant multiple. So it had to have had x sine y for that one. How would I have gotten a 1? Well, that one's easy. I would have had to have started with x. And now you can check if you take the partial derivative, you do get this first partial derivative. If I try again with this one, because that's not quite exactly right, my second try here is, how would I have gotten a function that when I took the y derivative, I get this? And the answer is, well, x is a constant multiple, so I would have had to have x, but I would have had to have had sine y, so when I take that derivative, I get back here. So that's the guess that I would have gotten just from here, and this is the guess that I would have gotten just from here. They're not quite the same. In fact, this x is maybe throwing things off. But let's be very careful. When you go backwards, you also have plus c. So don't forget the plus c's. And not only that, this is actually a c that is a constant as far as x derivatives are concerned. So this could be actually any function that has only y's in it. So it's like a constant function of y's. Okay, great. Over here, in order to take a y derivative and have this part disappear, it's not just plus c, it's a plus a constant function of x. It may not be the same one, so I can call this like constant function of y's and constant function of x. Now you try and put these pieces together. And your function, in terms of x and y, has to have all of those pieces. So I already have this common piece here. So that means that I will have that in my final answer. How about the rest? This one has an x, but this says I could have a function that has x's in it. So really that one there is going to line up with that one there. And so this x really takes the place of this. The cy, you look on the other one. Well, there are no things that just have y's in them. So really that one is just going to be 0. So I don't have any contribution to that one. And then really to finish it off, technically I could have just added any true constant. So that one there is a number. That function right there would work. And you should check. Of course, whenever you're doing these, I think you definitely should check. You take the x derivative of this like we just did. Well, sine y is like a constant now, so I get sine y with the derivative of x. I do get 1. Okay, that checks out. And then what happens if I take the y derivative? I'll get, well, the x is a constant in this one, so I'll get x cosine y. And that's it, because this x derivative will be 0 for doing the y derivative, so that checks out. So I did get back, so what's in the block works. Both of these derivatives apply to c, the plus c, that's just a true number. So building this stuff backwards can be, it gets harder. It can be a little trickier if these functions aren't so nice. Anyway, that's enough of me droning on and on, so if you guys are still awake and hanging in there, I think during the school year when they do this, they'll be like, you cannot turn your camera off. I don't know exactly how they're going to do it with attendance, like section marcher, how we're going to do a section marcher. It'll be interesting to see how that goes. So don't have rank, right? Don't be the senior guy in the class. You don't have to deal with all of that crap. Is it going to be paper section? This should be the opportunity where we turn section marchers into an electronic process. We are in the 21st century now, so come on, let's figure this out. Anyway, maybe we'll figure it out by the time you guys graduate or by the time I retire. I don't know. BMI is slow to move. Okay, 2 sections. That's nuts. And then this afternoon we're going to be doing another one. No, not today. Thank God. That's not today, right? Today is, what day is today? Is today Tuesday? I've lost track of what day it is. I think it is Tuesday. No, it's Wednesday. Yes, so that's not this afternoon. That's tomorrow. The days are blending together. Okay, I'll shut up. I'm babbling now. Questions on homework that you might have now that's jogged your memory?
Sir, can we do 18 on 11.4?
Yes. Please do get. Oh, okay. Okay. This is actually not too bad. So you're given the position function here as t and 1 over t squared plus one. Okay, and then you're told that the tangent vector at 1 is 2 minus 2 over square root 5 negative 1 over square root. Okay. So at least it is a tangent unit vector. So if I square it, this will be 4/5 and this will be 1/5. When I add them together, I get 1. So the length is 1, so that's good. Confirm that t is as stated. All right, well, it's good practice anyway. I got to find r prime, and then I have to find the length of that, and then I have to divide, and that will give me t. So if we want to go through this, might as well. So I have to take the derivative of t. That's 1. That's not too bad. Take the derivative of the second part. So I guess we're going to use a quotient rule. Maybe I can rewrite this as t plus 1 to the minus 1. Take the derivative of that using the chain rule. I'll get -1 t squared plus 1 to the -2. So that'll be the same thing as putting it on the bottom squared. And I multiply by the derivative of the inside, which is 2t. So if you're having a problem with the derivative, go back and work this through either quotient rule or chain rule. And so we get that. Now we have to find the length of that. So the length of r is the square root of 1 squared plus this fraction minus 2t over t squared plus 1. -2t over 2 t squared plus 1 squared. That'll be the length of r. Now, I could simplify this out and divide, but in this particular problem, I only need to worry about t of 1. So let's do as little work as we have to here. This is going to be r prime at 1 divided by r prime at 1's length. So instead of doing all the algebra and working this out, let's just plug it straight into here. So what happens if I stick in 1 into this derivative here? Well, I'll get 1, and then what is this fraction going to work out if I plug in 1? I will get -2 on the top if I plug in 1. If I plug in 1 on the bottom, I'll have 4. And I'll simplify that. It'll be 1 plus 1, and then it gets squared. So without doing all the algebra, because it's kind of a nightmare, I'm going to do that. Then I'm going to divide it by the length, basically by the length of that. So that's going to be the square root of 1 squared plus -2/4 squared. And you can plug it in here, or you could just say, well, I got to take the length of that. So that is 1 -1/2 is the vector, and then what's on the bottom? If I work out the bottom here, this will be 1 plus, so this will be 1/4. However one squared out, 4 over 16, or simplify it first to 1/2, -1/2, it's squared, so that's 5/4. So that's going to be the square root of 5/4. So it looks like we do a little bit of simplification here. We can flip that. So that fraction right there is the square root of 5 over 2, because I can do the square root of 5 over the square root of 4. And now I want to flip and multiply it on both of those. So you can either put it on the outside or you can put it on the inside. If I flip and multiply on the first one, I'll get 2 over the square root of 5. So we flip this as 2 over the square root of 5 times 1. What do I get for the second one? This will be 2 over the square root of 5 times -1/2. And -1/2 times 2 over the square root of 5. And so I get 2 over the square root of 5, -1 over the square root of 5. Check. That is confirmation of that is correct. Now, I don't know if that was the part you were interested in, but there is a part B. And so part B is technically to find the normal vector, which is a freaking nightmare because I have to take this and divide it by this, work out all the t's, then do the derivative of that, then the length of that, and then divide to give me n. So if you had to actually find n as a formula, that would be hard. But, I mean, it would take a while. It's just algebra intensive. But you don't actually need to find n at any point. You just need to find the normal vector that corresponds to this tangent vector. So you at least need to know that the normals and the tangents are perpendicular to each other. They're both unit 1. So I think that can help us out pretty quickly if we look at the graph. So if we try and plot this thing, t1 over t squared plus 1. I think the easiest thing is to say, well, that means that x is t and y is 1 over t squared plus 1. So if I replaced and got rid of, what do you call it, eliminate the parameter, this would be y equals 1 over x squared plus 1. And so I just need to plot that. So I plotted that. I mean, I only really needed at 1, but if I did plot this whole thing, let's see. At 1, if I plug in 1, I'm at a half. So that's the point that I'm actually at. Plug in 0 and at 1. If I plug in something like 2, I'd be down here at a fifth. And so if you get a good graph for what this thing looks like, and from alpha, or your calculator, or whatever you want, plot y equals 1 divided by x squared plus 1. Just so we can get the where the sort of curve is to all of this. Floyd. Okay. Sorry. Oh, and it's 1 over. I'm taking too fast. Again. Okay. That only shows it here. Here we go. So it's going to come down, and 1 is right there, and so it's going to be kind of curved. So let's go back to our thing here. Coming down. I think at 1 it's curved the other way. So I'm going to move it up here just so I can get that curvature. So it kind of looks like that. It's a little bit curvier at the top, but right here, the tangent vector, if you were to follow this, probably not too surprising that the tangent vector has a positive x component and a negative y component. If I gave you this picture and said, if you're traveling down this path, draw the tangent vector. The answer is it better be here. And I know that my graph is not quite steep enough to get this to work out. So the tangent vector there, 2 and negative 1. Now, without going through all of the algebra to figure out what n is, we know that the answer is it has to point perpendicular to this tangent vector. So that means either my normal is going to go this way, or it's going to go this way. It has to be perpendicular. And so the question is which one is it? And this is where the meaning comes in, is that n points perpendicular to the tangent, but it also tells you which way that the curve is curving. So the curve is coming down and it is curving towards the upside. So that means that this bottom one is not the normal. The one that we want is this one. That's going to be my normal, because it's kind of like a force. If you wanted to make it turn, you'd have to push this direction, and that would cause it to come down. And it would cause it to come down. If it caused it to turn down, it would just go the opposite direction. Now, we know that if you had a vector already, then the slope of this guy is like rise over run. So the rise and the run. Now, how do you get the perpendicular? It's the reciprocal of that. It's the negative reciprocal of that. So it's really the negative run over the rise. So instead of the x and y being where they are, they're reversed and one of them is negative. So that means that the normal vector at 1 is either you switch them and make one of them negative, so negative, negative, or you switch them and make the other one negative. So that would be negative 2 over squared. So just switch them so that the rise becomes the run and the run becomes the rise. And this time I put in like a negative, negative on that one. Here I just put a negative on that. So you look at which one is it based on the turning of it. I know that it's not the second one because that would go back to the left and down, whereas this one goes over and up. So the long answer to this is that you just need to draw the picture. You just switch the rise and the run and negate the correct one to make it turn the left one. but you do need the graph. If you didn't have the graph, the best you can say is, well, it's one of those two. I just don't know what the picture looks like. So roll it, flip a coin. You're like, I don't want to go through all the math. I'll just guess which one it is. This one seems reasonable. So I don't know exactly which part of your question was, but that answers all of it. So hopefully that helps.
Thank you, sir.
Any others? Okay, well, that's a lot. That's a lot for one day to talk about limits and continuity and open, close, and bounded, and partial derivatives and mixed partial derivatives, and all this notational stuff. But at least it's derivatives, so hopefully that gets your brain sparked again on that kind of thing. And so anyway, finished just a little bit early, but you can go work on that. Get all the past homeworks in. Get these homeworks in on time will be nicer. But, anyway, I'll grade everything as much as I can this afternoon. I think today is technically midterm, so I'll be turning in sort of midterm grades so I can show you approximately where you're at. But otherwise, I'd say go work on that stuff and enjoy the rest of your afternoon.
Thank you, sir.
Have a good day, sir.
Yeah.
Thank you, sir.